All right, let's look at ideal solutions now made with a volatile solute. So, like any solution, I have a solvent and a solute, but this solute is volatile. We looked at another video, or in another video, we looked at solutions, ideal solutions with a non-volatile solute, but this one is volatile. Okay, so in that case, I'm really looking at mixing two liquids. So on my phase diagram that represents this system, I'm still going to have my vapor pressure against composition, and the whole plot is made up for one temperature. I'll add that as a label. So the whole thing, oh sorry, not P, T. The whole thing is recorded at constant temperature, and that makes sense. Okay, now if I have my solution here in my vessel, and inside I have the liquid A and B, they are miscible, so I have my single one-phase solution, binary solution, ideal, and I put the lid on, so I have vapor. Now my vapor phase is also A plus B. I'm going to move this over and put another P here so that we still stay labeled. Okay, so the lid is on. I have a vapor phase in equilibrium with the liquid phase. Now, liquids A and B have two different boiling points, therefore, excuse me, at this temperature, which would be below their boiling points of both of them, because I don't want this thing boiling on me. I'm just got a solution here and I'm measuring the vapor pressure as I change the composition. The partial pressures of each are going to be different. So I want to put my two anchors on here, and I need to think about this for a second. So when the mole fraction of A is 0, then at this point reflects pure liquid B. And so I'm going to place pure liquid B right here. This is specific label to this point, PB pure. So this, and I'm just going to write in underneath here and show you that this is a table value for B at temperature T. So I would look that up in a table. What is the vapor pressure of pure B at that temperature? Let's say that liquid A is a lower boiling liquid. If A is a lower boiling liquid, A has a lower boiling point temperature than B, so that at this temperature, or any temperature, what can you say about their relative vapor pressures? If A boils, let's say easier if you like, than B, because it boils at a lower boiling point temperature than B, then at any temperature, would you expect A to be more volatile than B? Yeah, you would. A is the more volatile liquid because it boils at a lower temperature, so it's easier to put A molecules into the vapor from the liquid. And therefore, at any temperature, including the one that we're using here for data collection, the vapor pressure of pure A is going to be higher than that of pure B, and let's exaggerate it a bit so that we can see the differences. So this is the vapor pressure of pure A at that temperature T. And again, this is something that I can look up in a table, or maybe it's given in a problem. Okay? All right, now, how are these points connected? Well, they're connected through all of the solutions in between. And remember, these are ideal solutions. And so if I look here, I have pure B. Think about it. I have pure B in there. I have no A yet. And as I move from left to right, I'm going to add, drop, 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 more and more A. So my solution is becoming richer in A as I move from here to here. And what happens is the effect on the vapor pressure of B is to reduce it. Because as I add more A, I have less B available at the surface to go into the vapor phase. So I want to keep my eye on the prize here so that I have a straight line. And there we go. So this line is made up of points which are, well, X and Y. At any composition of solution, this would be the partial pressure of what? Of B, exactly, of B. How do I know it's B? Look at the extremes. This thing goes to 0 here where I have pure A. Oh, right. And this is the highest, the pure value, when the mole fraction of A is 0. So clearly this is B. It's connected to B, and therefore whatever's connected to my pure B, that's the line of partial pressures above all these. So these are partial vapor pressures of B above solutions with composition mole fraction of A as determined by that X. And so now this, just going to turn this for a moment to draw it. I want to keep it straight. And so that line, these are all the partial pressures of A above solution of these compositions, and the line that connects these two is the total pressure above solutions. And so really, this, let me cut into this here at a certain, for an example. Okay, so, whoops, let me put a point here. And let me drop. Okay, so I'm going to point here, here, and here. And just for ease of explanation, maybe in notes, I'm going to give this a number. I'm going to make this a Q, R, S. Oh, ended up with a T. I don't like to use variables that have physical significance, but anyway, Q, R, S, T. Okay, so maybe you can take notes and I'll just describe. So, my pointer. At Q represents the composition of my solution. So, above a solution of mole fraction A equal to whatever this value is, so above a solution of this composition, the partial pressure of liquid B in the vapor is not this value, pressures on my y-axis, but the corresponding y value. The partial pressure in the vapor above a solution of this composition that is of A is not this point, but the y corresponding to that point. And so let's do this. This would be PA above solution of Q. This would be, let's back up. That's PB. This one is PA, right, because it's on the A line, above solution Q. And this is the total pressure. Oh, my pen's running out. This is the total pressure above solution Q. It's neat, right? And it's all done at this temperature. Okay, so let's review here. So I have a solution of A and B closed at this temperature. The solution, the liquid solution, not the vapor, but the liquid solution is this composition Q. The partial pressure of B above this solution is this value. The partial pressure of A in the vapor above this solution is this value. And the sum of PA and PB is P, or the total vapor pressure above the solution of this composition in the liquid. Okay, some formulas. See if I can squeeze them in just here. Okay, formulas. So, oh, wrong pen. P, let's start with this one. PB. What is it? Can you calculate it? That partial pressure of B in the vapor mix above the solution of composition Q. It is a fraction of what B would be pure, right? Make it make sense. What fraction? What fraction? B, B, B. In the liquid, okay? So, in fact, this is the mole fraction of A. Let's put this here. The mole fraction of B in the liquid. Can you still see? Because it's a fraction, so the sums have to equal 1, but there's only 2 components, it's binary. So when you know one, you know the other because it's the difference from 1. So the mole fraction of B in the liquid is equal to 1 minus the mole fraction of A in the liquid. Okay? You know how to do mole fractions. Again, the name makes complete sense. It's that fraction of the total number of moles of the system but belonging to A, or in that case, B. So it's NB over NA plus NB. This one is NA over NA plus NB. How do you know the number of moles? Well, you know probably in a problem, and I think that was the example, mix together 100 grams of each liquid. Oh, if the liquid is not a mystery liquid, if you know what it is, then you have a molecular formula, a molar mass. So if you know the mass and the molar mass, you know the number of moles. And maybe you just know the volume and not the mass. Well, if they give you the volume, they'll have to give you the density. Okay, make it all work, make it make sense. Let's write the same thing for A. What are we doing for space? the partial pressure of, I can't say that word 3 times fast, can you? Partial pressure. PA equal to the mole fraction of A in the liquid. Yeah, I'm making a big deal about this, yes, because the mole fraction of A in the vapor is different. And we'll get to that in a second. PA pure. Where does this come from? Table or given in the question, right? The pure stuff. Okay. Sorry, adjustment. So I have this, I know how to get that. Oh, Dalton's. Yeah, so see how this is Raoult's law, this is Dalton's law of partial pressures. So P, the total vapor pressure above the solution, is the sum of PA and PB. What else do we need to know? Oh, what's the composition of the vapor? Oh, that's a neat one. Okay, so the composition of the liquid given by the mole fraction in the liquid. Let's move over here. How would you find the composition of the vapor? Well, you'll recall that we reasoned correctly together that the vapor should always be richer in the more volatile component, the one that has the lower boiling point, the one that has the higher vapor pressure. So, but how do I quantify that? I realize that the vapor composition is not the same as the liquid composition for that very reason, right? The vapor is going to be richer in the more volatile component than the liquid. And so the composition of the liquid is straightforward because I'm the one who made the solution, so I know how much volume and with density was mixed, or what mass, what compounds was mixed, and so on. So that's straightforward. These guys are out of a table, so that I can find that, I can find that. But how do I get the composition of the vapor? Well, the vapor is gases, and we know that the number of moles is directly related to the pressure from the ideal or perfect gas law. So we're doing lots of stuff here. Ideal gas law, Raoult's law, Dalton's law, all relying on the fact that it's ideal. So the composition, always given in terms of mole fraction. So let's say the mole fraction of A now in the vapor. So it's very important to further qualify whether you're talking about the vapor or the liquid. Always. For me, for you. Okay. To be clear. A mole fraction is, well, that fraction of the number of moles belonging to A. So if I knew, I would put number of moles of A over the total. But I don't know the number of moles of A. But I do know something that's directly related to the number of moles, and that is the, yes, the vapor pressure. PA over B. I know this is not new. This is not new. You will find this, all of this, in a first year book. Okay, so if you still have your book, look it up. Doesn't mean it's first year stuff. There's 20 chapters in that book. You know, we did 11. So there you go. So it's the partial pressure, which we find through this formula, over the total pressure. So see how it all flows? Like, you really need to know your mole fractions, what you're mixing together. You need to have data to start with, the two pures, whether they're given or looked up in a table. And then you need to figure out what your partial pressures are. And then from those, you find your total pressure. And then from their ratios, you find the composition of, the vapor, right? And that's it. Can't be asked anything else about this. Okay? So think about that question if you've forgotten it. It is, or if you're just landing on this new, think about mixing together 100 grams each of benzene and toluene. So It's assumed that you know those structures, so you can figure out what the molar mass, just with a periodic table. You would be given their densities, and you would be given their vapor pressures at that temperature, at the temperature of the problem. And from that, you should be able to determine what is the, you should be able to sketch. Don't put A and B. If you know the identity of the molecules, then write that. Make sure you are assigning, right? Make sure you know which one is which. You might be thinking, well, what if they don't give me the boiling temperatures? How would I know? You will know because you'll have the vapor pressures of the two liquids at that temperature, right? At the temperature that you're studying. So you should be able to sketch the vapor pressure phase diagram for the binary system of the two liquids. Assume ideal behavior. At this temperature, determine what is the, what is the value of any of these? What is the composition of the vapor above a solution of this composition? And what is the value of the vapor pressures and the total? Or quite simply, fill in, you could fill in the blanks. There's not a whole lot of words needed for this question, right? Okay, so that, in a nutshell, really brings together what we need to know about ideal solutions and Gauss's law for ideal solutions. Okay.